Good morning. I want to welcome you to the fourth plenary of the week, and I hope you have a very productive meetings as Jorge wish you on Monday. I have the honor to introduce to you to Dr. Christopher Sabine. He works for the NOAA Pacific Marine Environmental Laboratory located in Seattle. He is a professor of the School of Oceanography of the University of Washington, and he has several research interests like ocean acidification, CO2, Earth-sea CO2 exchange, understanding global carbon cycle and the role of the ocean in absorbing CO2, and the basin scale distribution of carbon. He is also a senior fellow at the Joint Institute for the Study of the Atmosphere and Oceans. He has won an award from the Department of Commerce, the Gold Medal for pioneering work on ocean acidification. He is a scientific advisor for many national and international ocean carbon programs, and he has published around 100 papers that has been an inspiration for many people who worked on the CO2 field. He also is a coordinating lead author on the new IPCC report on carbon. Also, he's a very collaborative person who is willing to help you every time you have some CO2 analysis issues. And I want to take the opportunity to thank him for all the help and intercalibration that we did in the past. So he's going to speak about ocean uptake of atmospheric CO2 and his impact on marine ecosystem. So welcome, Dr. Christopher Sabine.
Thank you very much for that wonderful introduction. I'd also like to thank the organizing committee for inviting me to come down here and speak to all of you today. So I'd like to talk a little bit about ocean acidification and the ocean's role in global climate change. I should acknowledge the fact that many of my slides that I'll be presenting and the data that I'll be presenting have been contributed from a number of my colleagues, and a lot of the scientific concepts have been contributed by many more. So in my outline, I figured with this broad audience, I should perhaps give a quick introduction to the ocean's role in controlling atmospheric CO2 and the resulting changes in ocean chemistry. Even though we've had sessions all this week that have been wonderful sessions on ocean acidification, I just want to give a little bit of quick background on that. I'll give the geochemist's perspective on the effects of ocean acidification on marine organisms with that qualification. But I hope to kind of get through that quickly and then spend the second half of my talk proposing some new work that I feel is critical that we need to start right away, and that is picking some key regions where we need to make long-term extended integrated studies in the open oceans. And the idea behind this is, and the take-home message that I want to try and convey to all of you, is that from a geochemical standpoint, ocean acidification is a real and predictable consequence of rising CO2. And that's the message that keeps getting put out there. But I'd like to qualify that today by saying that attributing observed changes in the ecosystem structure in the real world, out in the oceans, attributing those changes to anthropogenic CO2, I propose will be extremely difficult and something that we need to start working on right away. In particular, documenting the changes that we're seeing both in biology, the geochemistry, and in the physics as well. So let me just jump right into it with a figure that has been put up a number of times throughout this week. This is kind of the iconic figure of climate change and global carbon cycle change, showing the rise in atmospheric CO2 at the Mauna Loa station that was started by Dave Keeling back in the 1950s. We've seen for the past decade, CO2 has been increasing at a rate of about 1.9 ppm per year. And that's, of course, caused by the burning of fossil fuels and the anthropogenic release of CO2 into the atmosphere. The average for this last decade has been about 7.7 petagrams of carbon per year. Now, I give a fair number of public talks on this, and one thing I've found is that people have a difficult time comprehending exactly how much CO2 that is. You know, we all throw up the plots showing it rising in the atmosphere, but really how much CO2 are we putting out there? You know, I'd say, all right, it's 7 petagrams, all right. A petagram is 10 to the 15 grams. Okay, well, that's a lot of zeros, but what does that really mean? It's a billion metric tons. Okay, that a billion at least is a little more understandable than a petagram, perhaps. Anyway, so I've come up with an analogy that I've been using that I want to try out on you today and see how you feel about it. So the analogy I'd like to use is a railroad car full of coal. All right, so imagine a railroad car. It holds about 100 U.S. tons of coal, which is about 80% carbon. That railroad car is about 60 feet long, including its couplings. So the question that I ask people is, so how long do you think a train would have to be to hold just 1 petagram of carbon? And when I ask my students this or the public this, I frequently will get answers, 100 miles or 1,000 miles, or maybe it'll stretch all the way across the country. But it turns out that if you go through the math, that train would be 156,500 miles long, just holding 1 petagram of carbon. Now, to put that in perspective, the circumference of the Earth at the equator is about 24,900 miles. So that railroad train holding 1 petagram of carbon would wrap all the way around the Earth 6 times. That's a tremendous amount of carbon that we're putting out into the atmosphere. And that's just 1 petagram. Burning of fossil fuels has released 7.7 petagrams on average over the last decade. We also have to add into that deforestation. For the last decade, that number's been about 1.1 petagrams of carbon per year. That's actually decreased. During the 1990s, deforestation was estimated to be about 1.5 petagrams of carbon per year. But we're still talking about the destruction of about 73,000 square kilometers each year, which is about the size of Panama. So you put these together, that's almost 9 petagrams of carbon that we're adding into the atmosphere each year. So now that train holding 9 petagrams of carbon will stretch all the way around the Earth 54 times. Now, about less than half of that CO2 remains in the atmosphere. That's left gets distributed more or less equally between the land and the oceans. And, of course, for the rest of the talk here, I'll be focusing on the oceans. Uptake currently is about 2.3 petagrams of carbon per year. We've had a number of independent estimates to try and estimate how much CO2 the oceans are taking up. This is a recent compilation done by Nikki Gruber, published in 2009, showing that all these different independent estimates give more or less the same answer. These are estimates for the 1990s showing an uptake of around 2 petagrams of carbon per year. So tying that back to our railroad train, that's the equivalent of taking one of those hopper cars full of coal and dumping into the ocean at a rate of 1 car for every second. That's 1 railroad train car full of coal dumping into the ocean every second of every day of every week throughout the year. As a result, we are actually seeing changes in the chemistry of the oceans. This is some data. The red plot is, again, the Mauna Loa atmospheric data set from the Big Island of Hawaii. We can compare that then to the rise in CO2 from Station Aloha. This is a time series station that was established in the late 80s, early 90s, showing that in the surface waters, the CO2 seems to be increasing at about the same rate as the atmosphere. We see this pretty much everywhere in the oceans. The water obviously is much more variable. We see both seasonal variations as well as interannual variations. But over the long term, the CO2 in the water seems to be increasing at about the same rate as the atmosphere. Commensurate with that, we see a decrease in the pH of the oceans. Now that's because CO2 is what we call an acid gas. And I'm a chemist. I can't get up here without showing you a few chemical equations, but I promise I'll keep them simple. So the idea is just that CO2 reacts with the water molecules to form carbonic acid. This is an acid because it easily releases a hydrogen ion, so it's this hydrogen ion that lowers the pH of the oceans as we add CO2. But not all of that hydrogen ion remains as free hydrogen. Some of those hydrogens, roughly a third, ends up reacting with another ion in solution called carbonate ion concentration to produce a carbonate. So what we see is that over time, the pH goes down, the hydrogen ion concentration goes up, the pH goes down, and the carbonate ion concentration goes down. Now the carbonate ion is important because that's an important component for organisms that produce calcium carbonate shells. So calcium carbonate is produced primarily through organisms in the oceans. They grab a dissolved calcium ion, a dissolved carbonate ion, put that together, and that forms a solid calcium carbonate that I'm sure you all recognize from these beautiful beaches that we've been laying on. And we can assess the ease or difficulty with which organisms can produce that calcium carbonate skeleton using what we call the saturation state. Any of you that have been in the ocean acidification seminars over the last week have seen this omega term thrown around a lot. It's simply the ratio of the dissolved ions in solution relative to a saturation state constant for the different phases of calcites, of calcium carbonate. So this can form different crystal structures to form either calcite or Reaganite or magnesium calcite. And basically the way the omega works is when you have values that are larger than 1, then those minerals are stable in solution and won't dissolve. When you have values less than 1, those will tend to dissolve. And we'll be looking at omega values throughout the rest of this talk. But let me just quickly first summarize over the last 200 years. We believe that on a global average, we've seen a drop in pH of about 0.1 pH unit. Now you have to remember that pH is on a log scale. It's kind of like the earthquake scale, the Richter scale, in that it's a change of 0.1 represents actually about a 30% increase in the acidity of the oceans. Commensurate with that, we've seen about a 16% decrease in the carbonate ion concentration. And of course, our real concern is what's going to happen in the future, and projections suggest that by the end of this century, we could see another 0.3 or so drop in the pH unit, representing about 150 to 200% increase in the acidity of the oceans, and about a 50% drop in the carbonate ion concentrations. The reason we're worried about that, because I'm sure most of you probably could care less about the chemistry of the oceans, is the impact that that would have on the organisms. And there have been a number of talks over this past week describing various impacts that ocean acidification might have on the organisms. Just kind of a brief summary of that, because it's far too much for me to go through, is that in general, it's expected that we'll see a reduction in the calcification rates of organisms in the ocean due to higher CO2. Not everyone is a loser. There will be winners and there will be losers due to ocean acidification. There's suggestions that there might be increases in photosynthesis, particularly nitrogen fixers seem to do better in higher CO2 environments. There have been a number of studies on looking at the growth or production or lifespan of higher level organisms, and particularly looking at them in different phases. It seems in general that the juveniles and larval stages are more susceptible to higher CO2 than the adults, but there have been a few studies recently showing that even adults may be impacted in particular species. Generally, we see a reduced tolerance to other environmental fluctuations. There have been a number of wonderful talks here talking about synergistic effects of CO2 together with temperature, for example, that you may get one reaction when you only change CO2, but you can get another reaction, in some cases enhanced, in some cases ameliorated by commensurate changes in temperature together with the CO2. So we really need to try and understand all those impacts together. And of course, there's also significant shifts in key nutrient and trace element species that can have impacts on organisms. For example, it's thought that ocean acidification might actually make iron more available to organisms, but on the other hand, it also makes the copper more toxic. So we need to look at those. And so all of these individual impacts on individual organisms then would carry through into the ecosystem and have potentially important impacts on large-scale ecosystems in terms of biodiversity, on terms of food web structures, and even getting into the changing biogeochemical cycles and distributions. But it's important to note that this is a fairly new field, and while there are a lot of talks and a lot of great papers that are coming out about this, there's still a lot of uncertainty in looking at the impacts of ocean acidification. And in particular, most of the studies, if you've been paying attention, really are laboratory or based on small mesocosm studies. And they're also exposing these organisms to fairly abrupt changes in the CO2. So we need to have longer-term experiments that look at the impacts over much longer terms, and we need to understand what's happening out in the field. And that's kind of what I'd like to focus on with the rest of my talk here, is that while these laboratory studies are great, ultimately we need to know what's going to happen in the real world and in the real oceans. And in particular, I'd like to comment on the fact that ocean acidification is frequently presented as a much more straightforward consequence of rising CO2 than climate change. There are a lot of people out there that are questioning climate change, that have difficulty with the fact that while we know that CO2 is going up, we know that CO2 is a greenhouse gas and absorbs heat, it is very difficult to take observed impacts of that. For example, heat waves or floods or hurricane strength or any of the different impacts that are related to climate change, and actually specifically attribute that particular phenomena to climate change. And that's been a difficulty with that whole field of science. Well, I would argue that we've got basically the same problem with ocean acidification. While we know, and it's very clear, that rising CO2 will change the chemistry of the oceans, actually attributing any changes that we might observe in ecosystem structure to that rise in CO2 is going to be extremely difficult. And therefore, I would propose that we need to start working on making field measurements where we integrate together the chemical measurements, where we're specifically focusing on trying to isolate the anthropogenic component of any changes in chemistry, together with the ecosystem studies that are monitoring and documenting any changes in ecosystems. And unless we start that right now, because it's likely to take decades for us to actually document that when it comes time to where we start seeing significant changes in ecosystem structure, we're not going to be able to actually attribute those to rising CO2 specifically. So what I would like to propose to this community is that we need to focus on a few key regions to try and do these long-term integrated studies. And I'd just like to propose 3 areas that I think would be interesting for trying to do this. So the first one is the high-latitude oceans. So this is a map of the distribution of anthropogenic CO2 in the oceans as of 2008, our best current estimates. And what you see is, so this is the column inventory of anthropogenic CO2. So if you take each square meter of the ocean and you add up all the man-made CO2 from the surface to the bottom, this is what you get in moles per meter squared. And you see that the distribution of anthropogenic CO2 in the oceans is not even. We get much higher inventories, for example, in the North Atlantic. And in general, we see that the higher latitudes tend to have more anthropogenic CO2 than the lower latitudes. In particular, There's been a lot of recent work looking at this in the marginal seas and in the Arctic that's fairly coming out just now is fairly new work, but suggesting that the Arctic has proportionately more CO2, has a larger per area inventory of CO2 than many places in the open ocean. And so it's likely to be seeing impacts of this rising CO2 disproportionately. Of course, a lot of the seminal papers on ocean acidification were looking at calcifying species, planktonic species like the coccolithophores, showing a decrease in calcification of these organisms as we go to higher CO2 levels. And so if you look at this is a composite image from the CZCS satellites showing the coccolith blooms, and we shown in white here, and you see that typically these blooms seem to occur in the higher latitudes. We also see more pteropods and other calcifying organisms in the higher latitudes. So I would argue that calcifiers, at least the pelagic calcifiers, can tend to have a proportionately higher impact in these high latitudes where we're expecting to see the largest CO2 impacts. We also know from the chemistry of the waters that the high latitudes are much more sensitive to change. This is a plot of the Ravel factor, which is a measure of the buffering capacity of the ocean, the ability to take up CO2 and minimize the changes in pH. And the higher values here in the high latitudes mean that the oceans naturally are less able to stop that pH change from the uptake of CO2. So again, the high latitudes are particularly susceptible, and therefore I think would be very interesting for trying to study and look for early impacts of ocean acidification. Of course, the counter-argument to that and the downside to that is the fact that the high latitudes tend to be much more variable than, say, the subtropical gyres. This is a flux map showing the monthly changes in the surface PCO2 values based on an empirical model that was developed by Rick Weinkoff and others at AOML. And what you see is that in the high latitudes, we tend to see very large variations just from month to month in the carbon chemistry of the waters there. And that's significant because there's been some interesting work by Sarah Cooley and others in Woods Hole looking at trying to isolate when you might be able to actually distinguish a real CO2 change, a chemistry change from that noise. And so this is some work that she's been doing. So this map here shows the date from the modeling work when you would actually be able to distinguish a CO2 change from the natural variability. And typically what you see here is that as you get into the higher latitudes, that the date that you can actually clearly identify this anthropogenic change, this trend, tends to be much later in the higher latitudes than in the lower latitudes. And that's simply a function of the variability. These are representative plots showing here the omega, this Reaganite saturation state at Ocean Station Papa, which is at 50 north, compared to Station Aloha in the subtropical gyre. And you see that the variability is much larger at Papa than at Aloha. And because of that, you can actually see the change in around 2030, 2045 at Station Papa compared to around 2015 at Station Aloha. So the second region that I'd like to propose is the coastal waters. Now those are important for a different region, for a different reason, and that's because they tend to have a lot of the economically important species that we're worried about in terms of ocean acidification. There have been a number of studies done on various benthic organisms looking at the impact of elevated CO2 or on decreases in saturation state. And again, we see a wide range of different responses. For example, crustaceans actually generally seem to do a bit better in the elevated CO2. But then they don't really form these massive calcium carbonate skeletons. Other organisms seem to show this bimodal response, suggesting that they're well adapted to their current environment, and either an increase or a decrease in CO2 might impact them. But the strongest impacts have typically been seen in the corals and mollusks. And particularly in the coastal waters, a lot of these mollusks are economically important species. So we went out and we did a study in 2007 off the west coast of North America, trying to look at how ocean acidification is developing in the coastal regions. And we specifically went out during the upwelling region. So in the west coast of North America, in the summer, we tend to get these winds that come from the north, which drives water offshore and causes an upwelling. And the hypothesis was that this upwelling of deep water would actually bring acidified water up onto the shelf. So this is an example from that cruise looking at one line here right at the northern border of California near Point St. George in California. This is a plot of the temperature, a section from offshore on the left, onshore on the right, of temperature in the colors and density, potential density with the contour lines. And you can see this blue water, this cold, high-density water, encroaching up onto the shelf. That's a kind of a classic sign of upwelling that was occurring right there. We make a section then of a Reaganite saturation state, and we see that these cold, deep waters are actually undersaturated with respect to a Reaganite. That means that calcium carbonate particles exposed to these waters would begin to dissolve, and those waters were coming all the way up onto the shelf, and in fact were breaching the surface in this particular location. Commensurate with that, we see a decrease in the pH and very low pH values in these coastal waters. So the implication then is that this might impact those organisms that live in those areas. Related to that, we've been working recently with the shellfish industry, again in the Pacific Northwest. Shellfish oysters and clams are a huge business up in the Pacific Northwest. In fact, the commercial oyster hatcheries represent about $100 million per year industry and about 3,000 jobs. But there's been basically our shellfish industry is in a state of collapse at the moment. For the past 6 years in a row, there's been essentially no new recruitment of baby oysters along the Pacific Northwest. And we've been working with the shellfish industry to try and figure out what's causing that. And so these are some measurements from one of the commercial shellfish industries hatcheries there in the Pacific Northwest. And what they found was that during times when we have winds from the south, so these are downwelling favorable winds, that we tend to get lower salinities at the hatchery, and we get higher saturation states with respect to aragonite. And when the larvae are trying to settle and grow there, that they actually do fairly well. But when we look during times of upwelling favorable winds, so the winds from the north, then we see much higher salinity, we see lower saturation states of these waters, and that's when all these larvae seem to be dying and not able to settle. So it seems that the recruitment of new oysters seems to be very closely tied to this upwelling signal. And of course, the issue with the upwelling is that it brings up cold water, high CO2, low pH, and low oxygen. And so we're still working with them to try and isolate exactly which of these components is impacting the oysters. But they've actually done some studies now where they've actually taken some of these waters and they add sodium hydroxide to bring the pH up, and all of a sudden they get a great recruitment from those waters. So it looks like the changes in the pH and the CO2 are what's driving this problem. But even if we can make that claim, which I think is a fairly strong claim, there's still the issue of how much we can attribute that to anthropogenic impacts. You know, this upwelling has been occurring forever, and even though we showed that in our 2007 cruise that the waters that were being upwelled contained 30 to 40 micromoles of anthropogenic CO2, which significantly elevated the saturation horizon, bringing it up into the upwelling zone that didn't occur back in the pre-industrial, that it's still, in these waters, extremely difficult to see the anthropogenic impact. So if we go back to the work I showed earlier with Sarah Cooley, this is now looking at CO2. It's not a Reaganite saturation state, but it's similar. These are from some buoys that I've had deployed off of HOTS, shown here on the left, at the HOT site, and at the Station Papa, the same locations that we showed earlier with Sarah's work. The blue, it shows the surface water CO2 values. The red is the atmospheric CO2. And you can see that the variability in surface CO2 is a bit higher at Station Papa than at Station Aloha. This is consistent with what Sarah was showing from the model earlier. But both of these are still relatively open ocean stations. If we compare that to a mooring that I've got off the coast of Washington, this is on the continental shelf, so these are now all on the same scale. You can see that the variability in the coastal waters is tremendously larger than what we see in any of these open ocean sites. So actually attributing any changes that we might see in these data would be extremely difficult to attribute that to find the anthropogenic signal. And so this is from the continental shelf. We can even go in a little further. This is now in Puget Sound, where we see even larger changes that, again, would be extremely difficult to attribute to anthropogenic changes. The final example region I'd like to talk about is our coral reefs. You know, we've heard a lot about the impact of CO2, rising CO2 on corals, and they have been portrayed as the canary in the coal mine for anthropogenic CO2 and for ocean acidification. And that's because consistently we seem to see this strong impact of, as a Reaganite saturation state decreases, we see a decrease in the calcification rate of the corals. And there have been studies done by modelers. This is an example from Cow and Caldera showing that the surface saturation state of the globe with an atmospheric CO2 of 280 parts per million. All the little magenta dots on here are the locations of all the known coral reefs in the world. So this represents a pre-industrial ocean, and you can see that all of the coral reefs are growing in this area that's colored blue. These are the high saturation states. In fact, here we're showing a histogram of the distribution of saturation states that these different corals are exposed to. But of course, the corals can't move, and as we add CO2 and change the water chemistry, those corals get exposed to different chemistries. So we can step through, so this is the pre-industrial. Here's roughly where we are today. So you can see from this histogram that we've already moved into lower saturation state waters. And then as we move out into the future, these corals get exposed to lower and lower saturation states, to the point where it's been suggested that there'll be significant decreases in the calcification rate of corals by the end of this century, and that all of our coral reefs globally will be in trouble. Now, this is another way to look at this. This is some work from one of our students, Katie Schaumburger. And so now we're looking as a function of latitude at the Reaganite saturation state. The red lines show the present saturation state distribution as a function of latitude in the Pacific. The green line then is a doubling of CO2, and then the blue line is for a tripling of CO2. We can then take those saturation states and extrapolate them to the location of the corals, and this is what you would get. So because most of these measurements are all from the open ocean, so we have to extrapolate those into the coral regions. And so this is the distribution of saturation states that you would expect to see on the coral reefs. But it turns out that when you actually go out and measure it, and there are not that many studies that have done this, but there are a few, that in fact, when you actually go out and really measure the CO2 and the Reaganite saturation states on these reefs, they're much more variable than we would project from extrapolating open ocean measurements onto these local environments. And so the corals are already seeing what we would project as a doubling or a tripling of CO2 impacts in the waters. And so I think we need to look more closely at the chemistry of what's happening actually on these reefs to better understand the impacts that we might expect to find. This is not just in the Pacific. Here's a similar sort of example from the Atlantic. This is some work that Dwight Gledhill's been doing, where he's taken empirical relationships to try and estimate the Reaganite saturation state in the Caribbean. And here again you see strong seasonal signal, but generally over the last 20 years a decrease in the Reaganite saturation state. So we've, working with a number of different colleagues, established a testbed site right here in Puerto Rico at the Cayo Enrique Reef off La Paguera in the southwestern Puerto Rico to try and look at what the real variability is on those reefs. This is again showing the CO2. We see a very strong seasonal variability in the surface water CO2 that's over 100 ppm variability. You see there's a lot of this jagged up and down. That's not just noise in the data. These are real signals. So if I blow up just the last month of data, so this is actually from December, this last December, you can see that there's substantial variability on time scales of days to weeks in the surface waters that we need to understand that, I mean, this is the real world that the corals are being exposed to that we need to better understand. We can then take those data together with relationships based on salinity to look at changes in alkalinity. We can calculate then the saturation state shown here with the black dots. This has been corroborated with measurements of DIC and alkalinity made by Jorge Corredor's measurements here in Puerto Rico, showing a very nice correlation. And again, we see this strong variation in a Reaganite saturation state on a number of different time scales that's at least twice what you would predict from these large-scale empirical models. So again, the variability that we're seeing actually on the reefs is much larger than one would predict from the open ocean, and we need to go in and we need to study those and document those. So to conclude, the addition of about 150 billion metric tons of carbon to the ocean over the last 2 centuries has lowered the global pH by about 0.1 units. That represents a 30% increase in acidity, and that's going to expand into the future. Laboratory mesocosm studies show a range of responses to marine organisms to elevated CO2, but a lot of those studies have been in aquaria or in laboratory studies or even small mesocosms. We need to figure out ways to take those studies out into the open ocean to really document what's going on. There are 3 particularly vulnerable regions that I would propose need to be addressed immediately in terms of developing long-term integrated studies. That's the high latitude waters where we expect anthropogenic impacts on the chemistry side to be felt very quickly and are seeing already. We're already seeing in the Arctic, for example, seasonal periods where the waters are becoming undersaturated with respect to CO2. Coastal waters that are economically important for society, where we need to really understand what the impacts might be and how we can attribute those to anthropogenic CO2. And coral reefs, where we have seem to have particularly sensitive organisms that may be reacting to anthropogenic CO2 that we need to try and document and understand. So the variability in these 3 regions, however, in the carbon chemistry as well as in the biology will make it very difficult to attribute any observed changes in the ecosystem to anthropogenic causes. And therefore we need to start documenting and measuring these sites right away and develop a long-term program to try and document this. So, thank you very much.